Hello, everyone. Welcome to this new edition of the Frontier Seminars. This is organized by the High Energy Astrophysics Division of the AAS. My name is Javier Garcia. I'm part of the executive committee of the head. And this is a seminar series for those who might not be aware that it started back during the pandemic, and we have decided to continue to give opportunity, especially to young researchers and students, to promote their work. So it's always virtual, it's always on via Zoom. And we try to keep a cadence of 2 to 3 months for each edition. The committee is chaired by our Vice Secretary, Drew Miles, Caroline Kierans, and myself. And as usual, today we'll have 3 talks. I'll introduce each speaker before the talk. Each talk is roughly 15 minutes long, and we'll have questions after each one of them. And as you probably heard, this is being recorded, and we post the recorders online in the website, so you can always go back and listen to them, see them. So today, the first speaker is Thibault Lechien. He's from Max Planck Institute for Astrophysics. He's originally from Belgium and has a background in computer science, and currently is doing a PhD at the Max Planck Institute for Astrophysics, and previously did a year-long research project at NASA Goddard, which is the topic of this talk today. So go ahead, Thibault.
Hi, thank you for the introduction. Yes, so today I'll be talking. Hello, everyone. My name is Thibault Lechien. I'll be talking about how we can use multi-wavelength observations to do parameter inference for neutron stars. So this is the work that I did last year, and I'm now a PhD student working on a different topic, but we're close to finishing the current project. So there's 2 key questions that we're interested in. Where first is we want to learn more about the mass and radius of neutron stars. This places important constraints on the equation of state, which probes the fundamental physics inside of these stars. The second key question that we're interested in this talk is we want to know more about the magnetic field of a neutron star. Since it is shown that the magnetic field for pulsar JW30, which we'll be looking at as a case study today, is likely to be multipolar. And so the way that we try to answer these key questions is we observe these stars using space-based telescopes, such as the NICER instrument, which is mounted on the ISS. And as this neutron star rotates, these X-ray emitting bright spots on the surface come in and out of view. And this creates then a periodic light curve, which is basically just the photon counts binned over time. So that's how we observe these neutron stars. The way that we then try to infer information about these is we have simulations that try to model these light curves, right? So we have some model for this neutron star, which consists of like the fundamental parameters like mass and radius, and we also try to model the magnetic field. Then we do some cool photon ray tracing and force-free simulations to find out what the simulated light curve would look like. And I'll go a bit more in detail on how exactly this mass and radius is incorporated into these light curves, because I think it's really interesting, and maybe not everyone has heard about it. Namely, these neutron stars are so dense and compact that they bend light around them quite strongly. This means that if you look at a neutron star, you not only see the front side of the star, but the photons bend around the surface to give you a view at that's part of the sides and part of the back side of the neutron stars. So they're similar in black holes in that way, except they curve a bit less strong. But this means that if you look at a neutron star and let's say, if you would fix the radius and try to increase the mass, it would actually appear larger. Not because it's actually larger, but because you can see more of its surface at the same time. And this means that if you have these X-ray emitting bright spots on the surface, they will appear warped depending on the mass and radius. And so that's how this mass and radius information is incorporated into these light curves. And so when we then try to look at the observations and compare them with the simulations, we vary the input parameters and look for a combination of parameters that leads to a best fit to the observations. And if we do this many different times, we can use our favorite nested sampling or MCMC algorithm to then find a full posterior on the parameters. Now, the problem with this is that this forward model that has to do these photon ray tracing and these force-free simulations is that these are quite slow, right? So it's very hard to explore many different combinations of parameters, and so given observations, sometimes we're not really sure whether a different combination of parameters would have also led to a good fit. And it's not just our simulations that are slow. This is a very common problem. Basically, all of the recent work on pulse profile modeling runs into this problem, that their simulations are just too slow to be able to exhaustively explore the whole parameter space. And this is very dangerous because if you don't fully explore your parameter space, you can underestimate the uncertainties on your posterior, and you also can find biased posteriors. To give you an example, I made this toy model to illustrate why these slow forward models are dangerous. And let's say you only have like 5 million likelihood samples, which is considered very small for this problem, right? You would do one inference run with this amount of computing budget, and you would find the following posterior in mass and radius. And you're happy with this, right? You look at your convergence checks for your nested sampling algorithm, for example, and everything checks out. But then once you have more computing budget available to run more of these likelihood samples, you could find a completely different posterior. And this is just because you did not have enough likelihood samples in your first inference run, that you were wrongly you wrongly believed that the posterior had converged, basically. And so the way that we try to fix this problem is we try to replace this very slow forward model with a neural network. Namely, we train this neural network on millions of examples between input parameters and what their simulated light curves look like. And after training, this network has learned the relationship between these. So if you give it a new unseen combination of parameters, it'll be able to estimate what the light curve would look like up to a very high degree of accuracy. And not only is it accurate, it's millions of times faster than this standard process. And so if we would do nested sampling and batch GPU inference with this, we can reach up to billions of likelihood evaluations in just a day, which is really an unseen amount for this problem. And so now we can sample this very complicated multimodal parameter space in hours instead of decades, which is how long it would have taken with the very slow physically motivated model. In addition, we have a first paper out on this. This is Omschenk 2025. And in that paper, among other things, we show that using this emulator, it actually gives unbiased posteriors. So not only is it accurate, not only is it fast, but you can trust it to do inference. And what I've shown now is just looking at the X-ray light curve. But we would like to constrain this parameter space even more and head towards this multi-wavelength approach. And for this, we looked at the gamma ray light curves. So we also have Fermi gamma ray light curve observations for this neutron star. And the gamma rays can offer a very different view on the magnetic field. While the X-ray photons are emitted from X-ray emitting hotspots on the surface, The gamma ray photons are emitted are thought to have been emitted at a much larger distance outside the light cylinder in the current sheet. And so they offer the different types of information. And after synchronizing this with the X-ray light curve and using self-consistent simulations, so our models for the X-rays are is the same magnetic field model for the gamma rays, we found that actually the majority of the good X-ray simulate solutions actually do not fit the gamma rays at all. So here I show two examples of parameter combinations and magnetic fields that lead to great fits in the nicer X-rays. But if you look at how their gamma ray light curves are like, then they don't fit at all. And so this means that these gamma ray light curves can give extra constraining power on these parameters because we want them ideally to fit both the X-rays and the gamma rays, of course. And so what we find is, well, first, there is a solution that fits both the X-rays and the gamma rays. And if you look at then the posteriors, we find that the gamma rays are able to constrain the posteriors and strongly reduce the uncertainties when doing parameter inference. I can show you the full posteriors. They're very much too detailed to go into, but basically there's less green than there is red, which means we have constrained posteriors better with the gamma rays. And so in future work, this extra constraining power allows us to then include even more physically realistic effects and learn more about these. For example, we can look at the hotspots that can be temperature dependent, which we currently assumed to just be the same temperature. We can then possibly link this with the location of the radio emission, in addition to the X-rays and the gamma rays. And just to mention, an alternative to using these no-network emulators would be to use SPI. But this can often give biased posteriors, which is why we didn't use this in this work. But so in conclusion, we found that these emulators can be key to analyzing neutron star light curves because they basically amortize the computing time. We can now do new inference runs for different neutron stars basically instantaneously compared to our old method. And we find that these multi-wavelength studies can constrain the very large and complicated parameter spaces. On that note, I'd like to end my talk, and I'm open for any questions.
Great, thank you. And thank you for keeping the time almost perfectly. Yeah. So I'll open the questions session for Thibault. Anybody has questions, please raise your hand. While people think about it, I have a question. This is, first of all, very interesting because I think it's a very common problem nowadays. I come from the spectroscopy side, and we are at the point where we have models that you always want to put more physics, but every time you put more physics, you have more parameters. So I actually have a very similar situation. And I was wondering, for the number of parameters that you have, you mentioned 14 parameters, roughly how many individual realizations of your model do you have to include in your training set for the neural network? Do you have that number in mind?
Yes, that is something that we explored in the first paper that's out on the archive, and we find, well, it's pretty logical. If you have a bigger training set, then the no-network emulator performs better. So we saw that using roughly 50 million or 100 million led to good performance, and then there's also ways you can artificially inflate your data set by using data augmentation techniques. And so there are ways to improve this without running the physical model much more.
And can I just follow up when you said that the standard way was too slow? It's because you're computing the model on the fly while trying to do the fits, right?
That's right, yes.
So something we do in a spectroscopy, for example, is that we produce grids of models, and then we do linear interpolations, which is a bit silly, but it's a way to have complex models that take a long time to run to just be pre-computed, and then at the moment of feeding data, you can do it a lot faster by just interpolating. Is that something that your community ever explore?
Right. It's something we can explore. I don't think linear interpolation between different light curves would work very well here. In a way, these emulators can be seen as a type of smart interpolator. And
Yeah,
so
I'm not suggesting to do it if you haven't done it. I was wondering if you ever went through that intermediate step.
yes, of course, it's a way to think about the problem
Mm.
where the emulators are interpolating between the model outputs, but they're able to do this very efficiently and for very complicated data and output, which is why they're so interesting here. Yes.
We have one more question from Arnav.
Hi. Just real quick. So, do you think that there's some specificity here for neutron stars specifically, or because we have like a lot of Blazar and gamma ray burst data, so just quasars in like the same energy range? Could something comparative be done there?
Possibly. I don't think our physical model is directly applicable to those, but I think it could be interesting to look at possible extensions of this to other types of neutron stars. Yes.
Thank you.
We do have a question from the chat, if there's time, Javier.
Oh, yes. I'm just wondering if you use a forward model, I'm not sure what kind of computer you're using. You were talking about something about it could take decades to do a certain amount of simulated light curves, for over a finite parameter space. Couldn't you increase the fineness of the sampling and simply apply for more supercomputer time? I don't know if were you running this on like a desktop computer, the modeling, or were you using a supercomputer? But couldn't you get around that problem with the forward model of using a lot more like supercomputer time?
That is one way to get more likelihood samples is to increase your computing time.
Right.
To give you an estimate, we're already running on the physical model at least on 4,000 CPUs
Okay.
for thousands of hours on the NASA Pleiades supercomputer cluster. And even with that amount of compute, we still run into computational limitations. So what these emulators allow us to do is to not just improve the speed, but improve the speed by many orders of magnitude, which is able to resolve these limitations.
Right. Okay.
Thank you for your question.
Okay, thank you. I think we have to move on. Thanks, Thibault, again.
Thank you.
I'll introduce the next speaker is Andrea Gokus. She's a McDonald Center for the Space Science postdoctoral fellow at the Washington University of St. Louis. She did her PhD at the Riemeiss Observatory in Bamberg, in Germany, with Professor Jordan Wilms. She works in high energy variability of blazars, often also including multi-wavelength data from the radio and the optical bands. And one of the main projects is searching for gamma ray signals from high redshift blazars with Fermilab. Andrea, you are welcome to start your presentation now. Thank you.
Thank you, Javier. Yeah, so I want to take you on a brief journey into the past to about one billion years after the Big Bang. And so I will present my main results of a paper that is currently under review with AppJ. Now, before I start talking about that specific source that we looked at, I just want to catch up everyone on blazars. So blazars are a specific type of active galactic nuclei. All AGN are powered by accretion onto a supermassive black hole. and about 10 to 20% of all AGN are capable of producing very large-scale relativistic jets. And depending on what we see, the sources, the viewing angles of those sources, we see different features. And my work concentrates on blazars, where we have the relativistic jet pointed towards the Earth. So what we see, the emission that we see, is largely dominated by the jet. These sources appear very variable, and they can show very bright outbursts that we call flares. Now, blazars emit across the entire broadband spectrum. So it's important to take into account data from the radio up to the gamma rays if we can detect these sources at gamma rays. What I show here right now is the Blazar sequence, and all the high redshift sources that we see are more likely looking like the red ones in this example. So these are all flat spectrum radio quasars with their low energy hump of this broadband ACD being caused by synchrotron emission, and the high energy emission. It's debated, but following a leptonic model, this all comes from inverse Compton emission. And so my work concentrates on finding gamma ray signals from those high redshift blazars. I use FermiLAT. That's an instrument that has been orbiting the Earth since 2008. It's serving the entire sky, so we get basically an image of the entire gamma ray sky every day. The data is publicly available, and it works as a pair convergent telescope. So it's sensitive from about 20 MeV up to more than 300 GeV. And typically, new sources with LAT are announced through catalogs. There's a multitude of catalogs out there. The most current one is right now the 4FGL data release 4. And then there's also within the collaboration a group that's called the LAT Flare Advocates, where the daily sky is basically searched for new transients, and they release real-time flare alerts, for example, but also announce the detection of a new source. So this kind of approach works for detecting new sources for most sources. However, high redshift blazars are on average very faint with regard to the LAT sensitivity. Up to this date, there's about only 17 blazars at redshifts larger than 3 that have been detected. Some of them are reported in LAT catalogs. A couple of them have been detected with a different method, where not the overall entire time range that LAT has observed is average, but where we leverage the transient nature of blazars and look at shorter timescales. So basically detecting these sources during flares. And so I was involved early on in a search like this in the paper published by Greta in 2020. And so that work focused on the archival data, where we looked a posteriori for flaring high redshift blazars on time averages of 30 days. And we turned this basically into a project where we look at the real-time data that is coming in now, because the multi-wavelength data that we see, there is a lot of archival data for sources. However, during the flares, the emission processes might cause a change in the shift in the peaks and an increase in the humps, basically, that they go up. So in order to model the sources with a physical model, we need to have simultaneous data. So the goal of this search is not just detecting them at the gamma rays, but also having a multi-wavelength campaign. So just to illustrate this very briefly, so we have the LAT data. The pipeline that we use is automated. We monitor about 80 sources that we know that are high redshift, that are listed in the Blazar catalog in the BZ cut. We do an additional check for real signal from the source, since sometimes a false signal can sneak up on you. For example, I've detected some solar flares if the sun is very close to the coordinates of those high redshift blazars. And then the multi-wavelength campaign involves a variety of instruments from the radio up to X-rays, in particular the Swift, XRT, XMM Newton, and NuStar. And to date, we have detected 3 flaring gamma ray high redshift blazars. The most recent one was only March 2025, so that analysis of the data is still ongoing. The flare that we detected in 2022 is a source that is in the FermiLAT catalog, so it's bright enough that it was detected over longer timescales as well, and that paper is is already out. So this Texas 1508 plus 572. But today I want to focus on the data analysis basically that we did for this flare detected in 2023. And that source is actually also a source that had been identified as a high redshift source quite a while ago. It's kind of famous more or less for actually the X-ray spectra, but it also shows an extended radio and X-ray jet seen with Chandra. The jet exhibits superluminal, it looks superluminal, so there's you can measure the and constrain somewhat the Doppler boosting of the source. This one is not in any Fermi catalog. It was detected and reported as detected by two papers, Liao et al. In 2018 and the Creator 2020 study. And the X-rays were debated heavily, especially in the early 2000s. There was data taken with ASCA, with Rosat, Beposax, and the spectra show some very unusual excess absorption, or what it looks like. There's also some other theories that it could be more like bulk computerization of thermal photons instead of an absorption signal. And this source flared in December 2023, and we detected it with our pipeline, and then launched a multi-wavelength campaign that included SWIFT and NuSTAR for the instruments, so the X-ray satellites, and we also took data with the Radio Effelsberg telescope and some optical observations with Perkins and the Sierra Nevada Observatory. But since this is not a very bright source, we did want to make sure that the excess that we see is definitely coming from that source. So there's two, and you can see this signal in the Fermi data basically on the left here. It is spatially coincident with our high redshift Blazar, but there's two known gamma ray blazars close by. So we made sure with the light curve to check that it's not them, that they are flaring. And we used then archival and also our new data to verify for other counterparts that also are not detected in the gamma rays. The Fermi localization is not super great, so you can see that the uncertainty of the positions here is the best fit coordinates is very large. But basically in the X-ray and radio data, in the X-ray we see two sources, and then one of the sources, this 2-mass source here, is not a radio emitter, but GB6B1428 is very visible here. And then with our coincident observations with Swift XRT and NuSTAR, we do see this source very clearly as well. And so we confirm that this gamma ray signal is coming from this high redshift Blazar. So we did some Swift monitoring with XRT. It reveals variability on the timescales of days. And what was very interesting was also that the hard X-ray flux increased significantly during the flare, which, as you will see in a second, in the broadband spectral energy distribution, really helps to constrain the physical processes. Now, with regard to the X-ray spectra themselves, we do not find this strong excess in absorption. Now, it is above, so in this plot here, the galactic foreground absorption is marked here with this dotted line. Our 2023 data here with the solid lines, that's our best fit confidence region between the photon index and the absorption, shows that there is something that is in excess of this galactic foreground absorption. However, it's all not consistent with the NH proposed or measured by Boller et al. In 2000 based on the Rosat data. So it's unlikely that the intrinsic absorption has changed so much only within 20 years or so. And we would expect actually if the absorption is present, we would see this also as a strong signal, especially when the X-ray flux is brighter. So we think that it's more likely that the shape of the X-ray spectra could be coming from the bulk thermal comptonization that was also for this source suggested by Charlotte et al. In 2007. Now, this is the broadband spectral energy distribution. I wanted to highlight that this is the most distant gamma ray flare that we have observed to date. It's also the most distant gamma ray source that we know and we've detected with Fermilat. And as you can see, the high energy hump is fairly well constrained with X-ray and gamma ray data. Well, we don't have a lot of data for the synchrotron emission here, because that is mostly here in the far infrared, but we don't have any data that we can take in time with the flare. But our Compton emission here, you can also see that the NuSTAR data was very essential to constraining the inverse Compton emission. And this is a source that peaks at 1 MeV. So basically, this is one of a type of source coined as MeV blazars that looks like very typically like a high redshift blazar. And that is actually a very interesting source also for future MeV missions. Now, with regard to the little bit optical data that we have, we were able to measure polarization that was fairly high, which helped us to disentangle the contribution in the optical from between the accretion disk, where we don't really expect a high polarization degree, versus the synchrotron emission, where we do expect polarization. So that helped us to constrain our emission for the synchrotron component, basically. Now, to put this at the end in like a bit of a broader context of the entire high redshift or the blazar population and the luminous blazar populations, I have plotted here the redshift versus the Compton dominance. And sorry, I have to go back. So the Compton dominance is basically just the ratio between the peak of the synchrotron emission versus the peak of the Compton, inverse Compton emission. So this is just a ratio that tells us basically how much inverse Compton emission from external photon fields dominates over inverse Compton emission from that is produced by the synchrotron photons themselves. So basically what it tells us is if there's a high Compton dominance, we have more external photon fields that contribute to the high energy emission. And we do see somewhat of a trend here a little bit, which could indicate that at earlier times there might have been more the external photon fields, which can come from the accretion disk, the broadline region, or the torus, that they have been stronger in the early universe than at the very local universe. And at the same time, the Compton dominance is not for each source a fixed data point, but here I highlight both our source, the GB6B1428 as a star here. The MT symbol shows the Compton dominance in the pre-flaring or the quiescent state, and this filled symbol is for the flaring state. I added also the other source on which I published a paper last year, Texas 1508, and there's quite a significant increase during those flares. So the Compton dominance increase also makes it easier for us to detect those flaring sources with a gamma ray instrument. And in particular, again, this will be more sensitive towards MeV energies, where we hopefully have more missions coming up soon. And since I'm running out of time, I'll just leave you with my summary here. If you're interested in the other paper I published, here's the QR code, and I hope the other paper will be published soon. Thank you.
Thank you, Andrea. As before, please, if you have questions, raise your hand, or you can type in the chat. We'll monitor that. In the meantime, can I ask you? It wasn't super clear to me. What is your conclusion about the excess absorption? I thought you said that it might not be absorption, but it might be just the shape is produced by bulk comptonization. Is that correct? And if so, can you explain?
Yes.
How that works?
I mean so the soft energy range we cover mostly with Swift data. So ideally, so the sensitivity is not that great for seeing or constraining it that much, but in comparison with excess absorption versus the bulk comptonization, it looks like this would make more sense that this is coming from compensation of thermal electrons that causes the spectral shape to change. It might also be a combination that there's some absorption as well. With the data that we have right now, it's difficult to disentangle that. But for the flare, if the absorption would be that strong, we would have also expected to see this even more significantly in the X-ray spectra we took during the flare, because the X-ray flare at X-ray data or the X-ray flux was higher, and the absorption should be more present than that.
I see. Okay, thanks. I think there's a question in the chat. If that person wants to ask a question, or otherwise I can read it.
Yeah, I see it. Do you mean the ratio of electrons to protons? Because we assume equipartition there.
Okay, that answers the question. Yeah, that was exactly the question.
Can you actually repeat the question since we're recording?
Oh, sorry.
I'm not sure.
Yes. The question was, what is the matter composition of the jet that you're assuming it matters significantly for bulk quantization?
Okay, thank you. Elias?
Yeah, so hi Andrea. So well, first, great talk. Second, based on the bulk optimization. So I think from what I remember when I was dealing with all this, one way to test bulk optimization is to search for the variability of this component on the longer term, because from the works of Annalisa Ciolotti and Gabriele Ghisalini on that, they predict that this feature should be variable. So if during the flare you see something, maybe longer monitoring, soft X-ray monitoring could tell us more about whether this feature is persistent or not and how it's evolving, maybe. Not sure if you have...
That's a good point. So if I quickly go back, there is this. So we had the 2014 data where we have a NuSTAR observation and Swift observation. Now the Swift data was, I think, had a little bit of less exposure, so that was not, as you can see, you cannot really distinguish the values here between the 2014 and the 2023 observation. It does look like there's a bit of a change, but yeah, I agree that would be interesting to monitor longer term. Thank you.
Okay, I'm afraid we're out of time. So thank you, Andrea, one more time. And of course, you can send her comments, questions. So let's move to the last speaker of today, Chamani Gunasekera. I hope I said it correctly. Is currently a postdoc at Space Telescope Institute, working with the ISM research group on interstellar dose extension of nearby galaxies using HST and JWST data. So also working on Cloudy, which was the main focus of a PhD thesis. To defend her thesis at the end of 2023, and have worked on various aspects of Cloudy, including its dose grain depletion framework, the Chianti atomic database that incorporates, and the one-electron Lyman spectrum, which is the topic of today's talk. So go ahead, Chamani, you can share your screen, start.
Okay, can everyone see this and hear me okay?
Yes.
Okay, yes, so thank you for that introduction. My name is Chamani Gunasekera, and I'll be talking to you today about the physics and diagnostics of one-electron systems with Cloudy. So my current work is at the telescope in more UV optical spectra, and this work was part of my PhD thesis in collaboration with Gary Furland, who was my thesis advisor, Peter Van Hoof, Stefano Bianchi, and Masahiro Sugimoto. So I want to start with the motivation for this project. Let's see, one second. The CRISM telescope launched in September of 2023, and it has on board the microcalorimeter spectrometer, like Hitomi did, and we should be hopefully getting data for it now and probably last year as well. And because of its microcalorimeter technology, it has a super high spectral resolution and will be able to see X-ray features that were not resolvable before. And one of these super important features is the Lyman alpha features of the one-electron species. And here's a CRISM spectra of the Perseus cluster, and you can see on the top right corner the iron one-electron Lyman alpha doublets, which was not resolved before. It was a single peak. On the left hand, I have a plot that shows the resolving power needed to resolve the Lyman alpha doublet in red, the Lyman beta doublets in green, and the Lyman gamma doublets in blue. Now, of course, no current telescope or anywhere near future telescopes will be able to resolve the hydrogen Lyman alphas into its doublets, but the resolve spectrometer on board CRISM will be able to resolve the Lyman alpha doublets of the one-electron species heavier than argon. And so this was the motivation for this project, which was to develop Cloudy's one-electron Lyman spectra to match that of CRISM so that it can be used to study CRISM data. So Cloudy, for those of you that don't know, was developed by Gary Ferland during his postdoc at Cambridge. Shortly after, Peter Van Hoof joined him in developing Cloudy in 1993, and the both of them have been recently training the next generation of Cloudy developers. And Cloudy was originally developed for optical UV and IR, but we're now developing it further to be better used by the X-ray community. Okay, so Cloudy offers lots of benefits for the X-ray astronomy community. It is a self-consistently solved radiative transfer, plasma chemistry, thermochemical and ionization balances, and it predicts the spectra that a telescope will see. It simulates a very wide range of plasma conditions, and it's designed to encompass most astrophysical plasmas that we have in our universe. Because of its ab initio type calculations, it computes both collisionally ionized and photoionized plasmas, and it does this at all wavelengths. And then lastly, we use external atomic databases, which is used in our calculations to get our atomic data from. But this adds an added benefit that our atomic databases are decoupled from our calculations. And so updating them is super easy, and we don't have to touch our calculations to keep up to date with atomic data. So here I have 4 very different astrophysical environments: a planetary nebula, a supernova remnant, an AGN, and an H2 region. Although all of these environments have vastly different densities, temperature, ionizations, and so on, the one thing that remains consistent is how the microphysics of how light interacts with matter. These microphysical laws remain the same, and lucky for us, most of our universe is made of hydrogen, and hydrogen knows how to do only a few different things. So the philosophy of Cloudy is if we can replicate those few different things, we can replicate the light that a telescope will see. Okay, so then my project was to take what Cloudy already does, take the alignment spectra that Cloudy already computes, and what I want to do is resolve the alignment spectra into its fine structure doublets. On the top left here, I have an example of the Hitomi observation of a Perseus cluster, and you can see that it resolves the Lyman alpha of iron, like what we saw at the beginning of this talk. So to do this, first, I incorporated the J resolved, or the fine structure resolved energy, so that we can get the correct wavelengths, incorporating all of the different quantum mechanics effects so that we can get an energy accurate enough that matches CRISM's data. And then we need to determine what population densities populate the upper levels of these Lyman alpha transitions, or otherwise the NP states. Ideally, to do this, we want to incorporate the J-resolved states in the balance equations, but we ran into the problem of not having enough proton impact collisional data to do this fully with the balance equations. So the next best thing was to take the unresolved NP population densities that Cloudy already computes, and then divide them up according to the ratio of statistical weights for the two different J states. So having done that and spending 2 years of my thesis working on this, making sure all of the microphysical laws for these J resolved or fine structure resolved doublets are consistent. Here I have the final result of my work. This on the left here, I have a spectrum of the Perseus cluster, and I've shown here the Lyman alpha doublets for all of the different species that Cloudy calculates. And it actually does this for not just Lyman alpha, but it determines up to which n, or principal quantum number, it will resolve the fine structure doublet for, based on a default spectral resolution we set, which we set it to be 10 times better than what is projected for the Athena telescope. We've also incorporated a command in Cloudy where you can change this spectral resolution depending on your science needs. Okay, so that was all of the theoretical work. Now let's take a look at what we can actually do with this. So here I have a plot from a letter I published earlier this year. This is the Lyman alpha doublet of the one-electron iron from a high-mass X-ray binary, Centaurus X3, and you can very clearly see the two resolved Lyman alpha lines. Remember that I told you earlier that the two lines should go something like this ratio of statistical weights, and this should end up being something like Lyman alpha 1 should be twice that of Lyman alpha 2. But then if you look at this, these two Lyman alpha lines, you can see that the taller line is not twice the height of the shorter line, Lyman alpha 2. So what is happening here? So basically what's happening is that the Lyman alpha 1 to Lyman alpha 2 ratio is changing based on the column density, or it changes based on the column density. And so we ran a Cloudy model of CenX3, and we varied the column density, and that's the plot that I'm showing you on the left here. And you see that as you change column density, our line ratio is changing. And this gives us a good way to constrain the column density of these objects. And for this one, we found it to be approximately 10 to the power 22. So I want to introduce to you what exactly is happening in nature that is changing the Lyman alpha ratio when you change column density. So what we're seeing here is when we have low column densities, you see this plateau. The Lyman alpha ratio is remaining at around 2, and then it plummets down, approaching a value of 1 after about 10 to the power 2. And I should note that this is a model of a collisionally ionized model with cloudy. So this effect can be understood by looking at the Eddington-Barbier approximation. Essentially, this is an optical depth effect. At low column densities, the photons are not interacting as much and it freely escapes the cloud. And so it retains that 2-to-1 ratio of the statistical weights. As you increase column densities, these photons are being increasingly more absorbed and re-emitted at different wavelengths. And so as it goes through more and more interactions, the fluxes kind of retain the optical depth effects of where was last re-emitted in the cloud. And so the Eddington-Barbier approximation says the emergent flux is determined by the source function at the location where the line optical depth reaches 2 to 3 when integrated from the observer's point of view. So assuming that Lyman alpha 1 and Lyman alpha 2 reaches an optical depth of 2/3 at approximately similar conditions at high column density, the intensities of those two lines approaches 1 at these high column densities. And that's essentially what's happening. So here I have added in a plot that I am currently working on. This is based on what are known as BPT plots in optical astronomy, which are used to diagnose between different objects. And here I wanted to take a look at what would happen if we did the same kind of concept, but now with X-ray line ratios. So if you notice in the plot, I have on the x-axis the Lyman alpha ratio, and on the y-axis Lyman beta ratio. And as I increase the column density, the plot changes from the bottom right or bottom left of the plot to the top right of the plot. This gives us a great way of constraining the column density at these low column densities now. So essentially you can constrain the column densities using this, what I'm calling GHF plot after Gunasekera, Van Hoof, and Ferland. And you can use the right type of plot to constrain column densities at high column densities. And that concludes my talk. You can find more of my work on my website by scanning the QR code on the right, and you can find more about Cloudy by going to QR code on the left. Yeah, and most of my work will be part of the next big Cloudy release. And you can contact me with any questions in my email. Thank you.
Thank you, Chamani. Okay, questions for Chamani? As usual, I can start. So I found it very interesting that the ratio of Lyman alpha 1 and 2 changes with column density.
Mm-hmm.
I was wondering if, I don't know if you have looked at anything other than hydrogenic species. If do you think this effect could also take place in more neutral ions for the K alpha 1 2 doublet?
I have not taken a look at other species just because this project was largely on the one-electron species and resolving the Lyman alpha of the one-electron species. But I believe, I don't know about neutral ones, but if you look at the two-electron species that Priyanka developed for Cloudy, I believe that also has similar kind of optical depth effects that these lines go through. And so when you change column density, you're changing the line ratios and but this one electron one specifically gives a great way of constraining column densities.
Can I, again, if anybody has questions, please raise your hand or write it in the chat. I think there is one in the chat. I also have another question. I'll follow up later. When is the C25 to be publicly released?
That's a great question. Hopefully soon. I'm working on it. This is half of my time that I spend on. And so things have been a little bit slow, but we do have a candidate release. So feel free to grab the candidate release, test it out, and give us feedback. And I believe Gary's in the room here. Maybe he has a better comment than me of when C25 is due.
As soon as possible.
Exactly. Yeah.
As soon as Chamani can do it.
Right.
Got
I wanted to push you, not push you, sorry, that's the wrong word, to inquire more into, I don't know if you can explain better what is the actual effect because it's a change in the ratio. You're saying it's an optical depth effect.
Yeah.
What exactly is happening? Is that one line is being more absorbed than the other, but the energies are so close? I don't fully understand physically what's happening.
Okay, yeah. So when you calculate the line intensities for these lines, you would expect, so part of it goes like the ratio of statistical weights, right? And so because of the ratio of statistical weights, you expect that the Lyman alpha 1, so it's, what is it, 2 times 3/2 plus 1. So Lyman alpha 1 should be twice the height of Lyman alpha 2. So at low column densities, because they're not interacting with other things in the gas as much, they're escaping freely. And so they retain that ratio of statistical weights. But then when you increase the column density, they go through more interactions before they escape the cloud.
Right,
And
but I would have expected that because they're so close in energy, the overall, statistically speaking, the interactions are similar for the two lines. So the decrease is dramatic. From 2 to 1.2 is quite a lot, right? So
yeah.
I don't know if there is a better way to understand this, but I suspect, I'm asking just because I suspect we might be seeing something similar in more neutral ions in other systems, also with Chrism, right?
Yeah, I haven't looked at neutral ions. I feel free to email me and maybe we can share. That'd be super interesting to look at because I've only looked at the one electron species because that's what I've been working on.
Great. Yeah, I might reach out to you with this. Yeah. Okay. Any other questions before we end? We're already at the hour, so we have maybe time for one quick one. But if not, I don't see any hands up. Nothing in the chat. Let's thank to all the speakers today. Great talks. Thank you so much, and thank you everyone for joining. We don't have set a time or a date for the next seminar, but as I said at the beginning, it should be within 2 to 3 months from today. So I hope to see you again next time. Have a great day, everyone.